First of all, my name is Ellen Rathje from the University of Texas, and it is truly an honor for me today to introduce John Bray as the 2022 Seed Lecturer. I could sit here and probably take about 10 or 15 minutes and list all the technical accomplishments John has made through his career, but I know most of you already know those. So I've decided to take a different tact. And I really want to focus on the influence John has had on me as a graduate student 20 plus years ago, and all of the graduate students that he has mentored through the years. When Dimitris Zekos and I put together the nomination letter for John for this award, we reached out, well, first we looked at the list of PhD students, and we realized that about 12 of more than 30 graduate students were in faculty positions around the US and around the world. That's really a huge percentage if you think about it. And all of us signed the letter, the nomination letter, to really show that that really is one of the broadest ways that you can impact the profession is through your graduate students that go on to faculty positions, do research, and expand on the field. And so in preparing for this introduction, I reached out again to those same folks who signed that letter, because I wanted to really focus again on how John mentored us and helped us be successful. Well, I can only tell you that the emails started flooding in from all of the different graduate students. It was almost like a reunion as we laughed and reminisced about the way John influenced us. So with that as a little bit of background, I think we need to put my slide up there. I want to take you on a little history tour of mentoring by John Bray. So let me take you back first to Kirby Cove, 1994. This is a picture that was taken after a football game on the beach there with Golden Gate Bridge in the background. You may recognize a few folks. Kenichi Soga, John, of course, John Stewart, and that might be me or it might be Justin Bieber. I'm not 100% sure. But I picked this picture because I really think it illustrates the influence that John had. So first of all, the glowing graduate students and postdocs waiting for John's quotes and advice to come through. But also, remember I said we just played a football game. And if you know anything about John, he's very competitive. He loves to take his family and his graduate students on physically exhausting expeditions, maybe up Mount Diablo or whatnot. But also as graduate students, there were those mentally demanding journeys that he took us through during our research. But we always came out better on the other side because of that challenge. And they were because of various quotes such as, "What doesn't kill you makes you stronger," which is true. If you want anything worth doing, is probably hard to do. But my response was always, "But John, if it kills you, it kills you." I can't read it, it's too far away. You will make mistakes because you're human. That's okay. And I think that's something we all need to remember. None of us are perfect. We should forgive ourselves when we make mistakes and move on. Be a laser. Be focused. This one was for Dimitris, because Dimitris, I heard, was all over the place. Stay focused on one thing. It's really easy to be distracted by various things, but remember what your goals are. Be bright, not right. So sometimes it's better to be smart rather than just showing that you're right. And I think sometimes at home I need to remember this. Insert any and every sports analogy known in the universe, because if it's been said, John has said it, to motivate us to be better in our work. Oh, one more. Finally, you have a small chance if you apply for something, but you'll have zero chance if you don't. And I know that many students said that he encouraged all of us, realizing you've got to be in the game to win it, even if it's only a small percentage that you'll win. So again, that is only a small example of the way John influenced so many of his graduate students to be successful. I know personally, I would not be where I am today without the mentoring and friendship of John Bray. He is often the first person I call when I have a question, even today, 20+ years after working with him. So on behalf of all of your graduate students all around the world, congratulations, John, on the 2022 Seed Lecture, and we look forward to hearing your lecture. And now on behalf...
Thank you.
He's still taller than me. And now on behalf of the GI and President Bob Gilbert, he didn't want me to call him president, but I did, we want to present you with the official Seed Medal.
It's tough to follow an introduction where your best lines were already used by the person introducing you. Well, thank you very much. It really is an honor to present the 2022 H. Bolton Seed Medal Lecture. I'll talk about evaluating the effects of liquefaction. The honor is great in terms of the students that have worked with me, and I thank those students, Dimitrios Zekos and Ellen Rathje, and all the other students that participated in the nomination. I thank the awards committee, because that's a difficult choice, and I thank the board of directors for this great honor. Work doesn't get done without students, and students require support, so the National Science Foundation, Caltrans, Pacific Earthquake Engineering Research Center, as well as New Zealand, has participated in sponsoring the research that I'm going to talk about. PhD students make it happen. I'm only here because, and this is true sincerity, is they do great work. I've been blessed with having brilliant, dedicated, cool, and wonderful students, just incredible human beings as well as engineers. This work is going to focus primarily on the work of Franklin Olea, Daniel Hudibrat, and Zorana Mijek, but it's built on the work of Christine Bazai and Roberto Luque and Chris Markham. And it actually goes back to Rodolfo Sancio 20 years ago, and Commander retired Jennifer Donahue, Shade Dashti, and a host of others. And so this really is an award that's possible because of the students who do tremendous work. I was fortunate enough to take classes from the late Professor Harry Seed and have him as my initial advisor, and he was a wonderful instructor, a wonderful person as well. I didn't have a picture of him in action, though. I just had that university photograph. So Professor Idris was kind enough to share a couple of pictures of him, because when you think of the late Professor Harry Seed, you think about field case histories. And so it's nice to actually have some pictures of him in the field inspecting a fault. Yeah, hopefully he didn't find too many in me. And then the seismoscope that displaced during that. I'd also like to thank UC Berkeley. They not only helped train me, but they motivated me into really loving the profession, and my colleagues at UC Berkeley have really been phenomenal. We'll talk about liquefaction triggering, and we often see liquefaction triggering as a manifestation, such as a sediment ejecta, and it's nothing new. It happened in 1906. This is your first sand boil. Actually, Professor Boulanger and I first saw this at the approach to the Bay Bridge after the 1989 Loma Prieta earthquake. Those of you know that we have total stress. The vertical stress is constant, but because of the cyclic shear stress, we induce shear strains. A contractive soil under those shear strains will develop positive pore pressure. The positive pore pressure going up and nearly equaling the total vertical stress leads to a large reduction in the effective stress. And it's the reduction in effective stress that really changes things in terms of the soil response. We'll also talk about liquefaction triggering in terms of a factor of safety, where we have the cyclic resistance ratio, the capacity, over the demand, the cyclic stress ratio. But really what matters most to you is the effects of liquefaction. And it's really that reduction in the effective stress that leads to a loss in stiffness and a loss in strength, which then leads to buildings tipping over, such as the 1964 Nagata earthquake, as well as the lateral spread. In terms of the effects of liquefaction, it's one thing when liquefaction swallows your chariot. It's another thing when it takes your throne. But I pointed to that water line because it reminded me after visiting New Orleans that the flood was devastating in New Orleans, and the flood from liquefaction was devastating in Christchurch. People who had moved back into their homes witnessed a flood event with sand and water flooding their first floor, their rugs, anything that they had left on the floor, which if it was my kids' room, it would have been everything, because that's where they store things. The opposite side is fire. And I was touched personally by that in 1995 because I went to that area where I saw a young lady put down flowers where her parents perished because of the fire that was initiated by liquefaction. And we've been lucky to not have these kind of events, but we unfortunately will have it, such as when I talked with elderly people after the, in 1980 when I first went to the Berkeley area, the elderly who were alive at that time never called it the San Francisco earthquake, they called it the fire. And so we need to be vigilant when it comes to looking at the fire effects. I will focus today on liquefaction effects on buildings. Much of this started in Turkey, in Adapazarı, where we had quite a few buildings that tipped, like we saw in Nagata, but instead of them being clean sands, these were silty sands. And unfortunately, it's repeated again in other earthquakes. One of them is the 2011 Christchurch earthquake in New Zealand, where we have fine sands and some silty soils that liquefied and led to punching failures, differential displacement, and sliding. In terms of mechanisms, this example is outstanding because we have a pile-supported multi-story building that has its seat of settlement, its neutral plane, well below the liquefiable material. And so it did not displace. But the hydraulic fill surrounding this building settled 300 millimeters, 1 foot. So that is a volumetric recompression because of liquefaction. This 3-story building, which is on a shallow mat foundation, punched 400 millimeters into the soil that had settled 300 millimeters. So the total settlement of that building is 700 millimeters. So that's 2 mechanisms for the building-induced movements. So in terms of displacement mechanisms, we have these shear-induced displacements, which are like a bearing capacity or an SSI ratcheting. I will not talk about that today. In fact, I talked about that 5 years ago for the Ishihara lecture, and that's in a paper with Jorge Macedo in Soil Dynamics and Earthquake Engineering. I will talk about volumetric deformations because that is another important piece to add to that, and it can lead to settlement that affects buildings, especially if they're close to a body of water. And that's largely due to sedimentation after liquefaction and post-liquefaction reconsolidation. And then there's the obvious thing, but the very difficult thing of understanding ground loss due to ejecta. If soil that was beneath your building is now on the ground, something's happened. It's taken that away and you've lost soil, you've lost support, you're going to get settlement. And so I will talk about post-liquefaction volumetric-induced settlement, but I'll also talk about ejecta-induced settlement. I do want to point out that most of this work would not have been possible without the START, and the START is GEAR, the Geotechnical Extreme Events Reconnaissance Association, which NSF has supported for now about 20 some odd years. And it is an organization that is you. If you're not a member of GEAR and you want to learn about earthquakes, sign up for GEAR, because That's how we learn so much. We record, we learn from nature, and then we try to figure out what we saw. A big part of the last 20 years is the movement from understanding liquefaction of clean sands to understanding liquefaction of silty soils, so I'll spend some time on that first. The 1999 earthquakes, Kocaeli in Turkey, as well as the Chi earthquake in Taiwan, were important in terms of silt liquefaction. Previous earthquakes had some of these cases, but they were largely clean sand, and so that's where the profession focused. We realized silts could liquefy. That was something that was actually debated in the 1990s, not debated anymore. We do not use the Chinese criteria anymore. It's unfortunately in a state-of-the-art paper that was published 20 years ago, but no one on that authorship uses that criteria. You should not use it, because the percent clay size is not reliable. We should instead focus on what Casagrande focused on, mineralogy, and use plasticity index as an index of clay mineralogy and how much clay is around. And we should also look at sensitivity, because those soils susceptible to liquefaction will typically have high water contents to their liquid limit. And let's do laboratory testing, because these cases are not well represented in some of our field methods. We can sample these if we take the care. If we use something like the Dames and Moore hydraulic piston sampler, or we use the gel push sampler, we can sample these soils, and we can test them in the lab to understand their engineering response. If we look at the engineering response of this soil, just in terms of what it means, in terms of the response of the soil and how the building might respond to that, notice these are simple shear tests that were performed by Dr. Donahue on adipozori silt. They were silt that was brought back to Berkeley so that we could test it very systematically. The baseline soil had a PI, plasticity index of 10. That's shown as these light black line in the background. And on top of that are initial and some additional cycles of loading in terms of shear stress versus shear strain, so the engineering consequences of whatever you want to call it. You can see obviously a PI of 11 essentially is the same, but a PI of 2 and a PI of 7, very little difference. So when I look at liquefaction effects and I look at those stress strain curves, I think I should look at them all the same. A low plasticity silty clay acts much like a very low plasticity or a non-plastic clay. Once you get up to a higher PI, then it becomes very clay-like. So there's sand-like behavior, there's clay-like behavior, and there's this intermediate behavior that's transitioning, but in many respects, to be conservative in terms of stress-strain response, it's reasonable to look at them as low plasticity, non-plastic silts as being very similar. Now, Christchurch came along. Now, when you first go to Christchurch, you focus on these manifestations that are extreme and severe, and it catches your attention. And so we focus there. And then after a couple of years, we realized, but there's another lesson to be learned here in performance-based earthquake engineering. There were sites that are tools that work so well in predicting liquefaction, essentially said, there should have been liquefaction there. We should have had extreme manifestations of liquefaction, and yet nothing happened. Now, one of the issues in terms of Christchurch, it has very uniform soils, and it has fine sands, it has silty sands, and it has silt. But I'm going to argue that they are essentially very similar materials. If you take a material that's uniform and it has the same mineralogy, the same particle shapes, it's the same material, but you just make the particles a little bit smaller and it moves horizontally on this graph, is that going to change the fundamental aspects and response of the soil? I think not. And so this is a case where fines content is not going to capture the key aspects of soil response. And I go back to, does soil know the 200 sieve even exists? It's good to sometimes think like a soil. When we look at Christchurch, and I've gone back, Professor Mitchell showed us this in the 273 soil behavior class in the old days, but a scanning electron microscope is insightful for actually looking at the grains. These is a clean sand in Christchurch. This is a silty sand, and this is a low plasticity silt that all have their images increased by a factor of 200. We've also divided this into the coarser, that's retained on the 200 sieve, and also the finer that passes through the 200 sieve components. When you look at it as somebody just thinking about discrete element modeling and particles, these particles all look about the same. They have a very similar distribution and shape. You would think that they would respond the same. And they would maybe respond differently than some of our classic testing sands, such as the Monterey 030 sand. Now, in a very classic paper, and one of the great things about working in Christchurch is I got to know Professor Chubanowski well. And through learning about Professor Chubanowski, I learned a lot more about Professor Kenji Ishihara. And I learned a lot from the late Professor Harry Seed and other people in the United States, but Professor Ishihara is just a tremendous intellect, and Professor Chubanowski has learned well and extended some of these things. They realized in 2002 in the Soils and Foundation Journal that they could characterize the state of sand and a silty sand using Emax and Emin, using the maximum void ratio, the minimum void ratio. They could use the concept of relative density even for soils that had more than 5% fines, which the Japanese standard is supposed to be restricted to. In the US, we're up to 15%. They looked at that and used this kind of statistics to prove to an unready audience that, no, we can use relative density beyond 5% fines. We can go to 30% fines. Then when I met him, it was more 30 to 40% fines. And after working together, we started realizing, if you really look at the data, you can go to 70% fines. So when Zorana started her work, Zorana Mishek, we said, we want to have a way of characterizing these silty soils as we transition from clean sands to silty sands to non-plastic silts. Let's use relative density. Now, one limitation is the Japanese standard method requires more soil than what we had in the retrieved specimens to do simple shear testing. And so she had to actually develop an alternative method for measuring Emax and Emin. We normally use a bigger hammer in the United States. Now it was time to use a smaller hammer and a smaller device, scale everything properly, and after many attempts, develop an alternative method that got repeatable Emins, which are shown in green, and Emax values that were consistent with what the Japanese standard method got. Now, this was done with materials that she had mixed, so they had enough material. But before she mixed them, she actually did tests on individual soils that were similar, that were going to later be mixed, and she got very repeatable results. Those are shown as the crosses. These are the Emax values. These are the Emin values. And so this work demonstrates that we can retrieve a soil from the field, we can perform testing on it, and then we can later determine the Emax and Emin from that limited amount of soil and gain a lot from that. Now, when we look at the testing, and this was the first testing, simple shear testing done on undisturbed, retrieved Christchurch soils, clean sand, silty sand, low plasticity silt, all at the same relative density, plus or minus, and their responses look very similar. This is the vertical effective stress decreasing as you cycle, and that's because of the increase in pore pressure. This is the stress-strain relationships. When we look at the cyclic resistance ratio of the Christchurch silt, this is that silt material at a relative density of 75%. This is at a relative density of 95%. And so we're seeing things that make sense in terms of sand-like behavior. If we take the cyclic resistance ratio from the lab test, we adjust it so that we get the field value. It's very similar to what most of the methods calculate from the CPT. And both of those values are well short, much less than the demand. And so these soils liquefied, but yet we have no manifestations of liquefaction. So we're going to have to explain that. One of the ways of explaining that is to look at simple things of saying, I will look at sites that have undergone different levels of shaking, because remember, there wasn't just the Christchurch earthquake, there was the Darfield earthquake, the June earthquake, the December earthquake, and let's just look at the profile of tip resistance versus depth, something called the soil behavior type index, which is calculated from tip resistance, and the friction ratio. Look at it versus depth at these different levels of acceleration. And I would like to focus on ISSMGE because that's where the clue is. If we notice that the red are sites that exhibited ejecta, and the blue are the sites that did not exhibit ejecta, what we see is all the sites at these levels of acceleration that had ejecta were thick deposits of clean sands that had soil behavior type indexes less than 1.8. The other sites went back and forth. They were highly stratified soil sites that had some layers that liquefied, but they were surrounded top and bottom on soils that did not liquefy or restricted flow. And so it's back to the geology. Christine looked at the 1850 maps and saw that the sites that did not exhibit ejecta were in these backwater swamp areas. In fact, Christchurch, there's a book called Swamp to City. This is what Christchurch looked like. And so these swamp areas are the areas that have these layered materials. This is important to do. We had done careful testing and sampling for that testing. We had done many CPTs. We had worked with UT Austin and done shear wave velocities, P wave velocities. We attacked this many different ways. We said, let's go back and just do continuous high quality sampling and let's log every hole to understand what the soil actually is. If you take this sample and you send it to the lab, you'll get a silty sand. It's not a silty sand. It is a sand and a silt layer, and a sand and a silt layer. This is what the reality is. When we looked at stress strain curves for these different materials, we don't see a big difference. So it's not that side of things. But when we did the post-liquefaction reconsolidation tests, obviously the sand reconsolidates quickly. The silt is slow. And then you break open the samples and you realize, as opposed to a clean sand where the water communicates vertically very easily, here, even at the element level, even at the laboratory test level, we see layers of silt and sand, silt and sand. So we're not going to have the same flow through this layered material than we would through this sand. And we just need to go back and look at the classics. Professor Youd and Perkins talks about the sedimentation process, the age of deposition, geologic history. And in his very famous paper, the late Professor Harry Seed in '79 said, just a single layer of relatively impervious sand or silt would completely invalidate the results of a pore pressure dissipation computation for vertical flow that was made without it being there. So the complication of the geology needs to be considered. Bringing those lessons home, I had worked in New Zealand for a number of years, and we also worked on trials with Tonkin and Taylor and the New Zealand government. There was an opportunity to do ground improvement at Treasure Island in San Francisco. This was a team from NGO as well as a number of Berkeley professors, and it was a great way of understanding, okay, how are we going to improve this liquefiable fill shoal material, which is on top of the Young Bay mud, on top of the older sediments. A Japanese contractor had a very energy invigorating method, vibrocompaction, using the direct power compaction method. And they brought that device over from Japan and said, we will densify that material. We will mitigate the liquefaction issue. Some cells were set up for various spacing of way to do the improvement. The blue CPT, this is the trace of the CPT in blue, is pretty constant over this area, and that is the pre-improvement CPT. And then we have the post-improvement CPT in red and green, 17 and 31 days after the improvement, respectively. And what jumps out at you is good improvement in the upper part of the fill shoal, no improvement in the bottom part of the fill shoal. Why weren't we improving these materials? They had similar tip resistances from the CPT. They had similar ISSMGEs. It's because it's a fill, hydraulic fill, on top of a naturally deposited shoal material. And the test was telling us something. We could not densify that material because it was not going to get densified. We did look at the relationship which works most of the time in terms of a relative stiffness. Probably the most important measure to get from a soil is the tip resistance. Far better than the unified soil classification system because you're learning how the soil actually responds to a tip being penetrated into it. Cavity expansion theory and other methods can be used to really gain good insight. The second most important thing is shear wave velocity because you get stiffness. And that relationship between shear wave velocity, which could be converted to shear modulus, and tip resistance gives us normally a sense of microstructure, cementation, and bonding. Soils up in here tend to have structure. Soils in here are, quote, ideal for the way that we analyze them. There's a hint that they're slightly different, but nothing conclusive. So we're going to do testing, but let's go ahead and do continuous sampling and log it. The hydraulic fill is largely clean sand with some non-plastic silt. Water can flow easily, it can vibro-compact. But the shoal deposit is actually worked over by nature. And when the sea level was lower, we had wave action. We had animals living in it. We have little burrows that are filled with holes. It's very erratic. When you look at the clay, high plasticity clay, it's not high plasticity clay like Young Bay mud. It is clay with silts and sand lenses in between. It's microstructure on microstructure at every different level. And in fact, if you go even deeper and look at the scanning electron microscopes, you see little bricks that are kind of fitted into each other with clay bonding them together. Something the cone can penetrate, but does not reflect the actual cyclic resistance ratio of the material. So relative density, I think, is a very useful way of looking and characterizing non-plastic soils. But the depositional environment, the soil system, has to be recognized because it plays a big part into whether a site will have or manifest liquefaction. And then continuous sampling with careful logging is a valuable tool. Now let's move on to post-liquefaction volumetrically induced settlement. This is a classic chart. We had a liquefaction workshop at Berkeley that a number of you went to back in 2016 in November, and we talked about this chart. It's incredible how Professor Ishihara and Yoshimi were able to take laboratory tests and use something at the factor of safety against liquefaction triggering, relative density, estimate a volumetric strain, and with that volumetric strain and thickness of each layer, you could add up the total contribution of the free field 1D settlement. That is based on probably the highest quality testing I've seen, 200 tests, cyclic simple shear testing, water pluviated, but all the tests were done on one sand, Fuji River sand. Are we sure that every sand in the world and silty sand is going to respond like Fuji River sand? So we've been using a method that is based on one sand as a basis for many of our methods for estimating post-liquefaction volumetric settlement, where we've applied them to many different sands, and we've also hoped that the fines content correction or ISSMGE correction to turn a silty sand into a clean sand works in this arena. And there's no assessment of uncertainty. So this is largely the work of Franklin Olea, who then developed a laboratory database. So added 9 clean sands to the great data set that Professor Ishihara developed, 3 silty sands, 5 silts, 2 gravels. Most of these soils have uniform distribution, so that's an important caveat, but they have different shapes, different confining stresses. We ended up with about 600 volumetric strain data points, 300 shear strain data points, and we're thinking this is a more robust way of developing a model post-liquefaction volumetric strain. Certain trends, fairly consistent with what Professor Ishihara saw. So let's look at volumetric strain trends in terms of relative density. They're largely a function of the maximum shear strain, especially as you're approaching liquefaction, and clearly after you exceed liquefaction when you get the larger strains. The type of loading or the confining pressure within this range doesn't make a big difference. With this idea that we can use relative density as a unifying factor for all non-plastic soils, we're going to be bold enough to put clean sands, non-plastic silty sands, and non-plastic silts all together. And the lighter line shown, or the lighter data points, are the Ishihara and Yoshinimi data for relative density of 73%, which is within this range. This is the data that we added from these other data sets in this range. Everything's fairly consistent. When we go to silty sands, and I show all the sand data in a 70 to 80% as light here, this is consistent except for this one data set. Why? Well, all of these gradations have coefficient of uniformities, D60 over D10, less than 4. They're uniform. Whereas this soil is well graded, and it has compressible, crushable soil fines. And so we cannot deal with that with this method. This is a different type of material, so we should put it to the side, and that means this is only restricted to uniformly graded materials. But a uniformly graded non-plastic silt is very consistent with the clean sand and silty sand data. We'd like to move beyond relative density because we know it falls short. It's not looking at confining pressure effects. A better, richer parameter is the state parameter that Bean and Jeffries introduced in 1985. And so we have fewer data because it takes more work to establish a steady state line. But with the limited data that we have, we see trends where the volumetric strain increases with maximum shear strain, and then it levels off with a limiting strain. This is what we have when we have a more contractive material relative to this more dilative material with a negative 0.2 to negative 0.15 initial state parameter. I've put relative density next to each data point, and you can see that this state parameter has promise. It's bringing things together and saying there's more to this problem than relative density. But the big problem here is we only have about 1/5 the data for the state parameter because many laboratory people do their work and then they do not take the time to establish the steady state line. If you want your data to be used in the future, you have to establish that steady state line so that we can go beyond relative density. But we like data, so let's go back to where we have a lot of data and look at the relative density model. And so this is the proposed model, 30% relative density all the way to 90% relative density, volumetric strain versus maximum shear strain. And the trends are pretty close to what Ishihara and Yoshinimi did. They did very good testing, and it turns out that Fuji River sand is kind of in the middle. So we've been very fortunate all these years. It was important to investigate this. There are changes. We see that the spread is a little bit less spread than what they had, and there are important differences at the boundaries. But if your soil has a relative density of 50%, you're going to get the same answer with our model that you would have gotten with the older model. I think the future is this state-based model, and so we have less data, fewer data points, but we're going to go ahead and still come up with a relationship that estimates volumetric strain versus maximum shear strain with different state parameter values. And obviously, these are the more contractive materials. These are the more dilative materials. The major limitation is the reduction in data. Besides volumetric strain, we should look at shear strain potential. That affects lateral spreading and lateral movements. But also, shear strain is the input to estimating volumetric strain. They have most of the data here, the work by Professor Ishihara and Yoshinami. We added data in terms of the clean sands and the non-plastic silty sands and non-plastic silts. The data is relatively consistent, and so we developed a model for a relative density-based model. It's based on a wider range of sands and silts and non-plastic silts. We did not feel comfortable developing a state parameter-based model because there just wasn't enough data to do that. Now that we have a model, and it's only a model, it's based on experiments, and it's a range of different soils, but it's a model of reality because we're doing an element test as opposed to thinking about the true field cases. So the next thing to do is develop a database for liquefaction settlement field case histories. This is developed again by Franklin Olea, 213 field case histories of liquefaction-induced ground settlement. Most of them are natural soil sites, but we also have hydraulic fills. And we thought they should be different because they're built differently. One is pluviation through water, hydraulic fill. The other one is sorted techniques by geology and geomorphology for building them. Most of the case histories, 3/4, are actually from Christchurch, because the most difficult thing in developing this database is getting reliable estimates of the ground elevation before the earthquake and the ground elevation after the earthquake. Those earthquake sequences, as well as the Kaikoura earthquake, had very good LIDAR measurements, and so we were able to get that information. One of the classic ones is the Marina District in San Francisco in the 1989 Loma Prieta earthquake. The U.S. Geological Survey did CPT work, but before then they did very careful measurements of settlement. So for example, in this location, which is characterized by 4 CPTs, and I show their tip resistance, their ISSMGE, their factor of safety using the Boulanger and Idris method, and the LSN value by Short Van Balagoy and others, 2014, to show that they're very similar in terms of characterizing the soil, and the response in terms of settlement is fairly similar, 50 to maybe 125 millimeters of settlement in this zone. There are other places where the settlement was negligible and the ground conditions were different. And so this whole area developed 4 sites for that one earthquake. The Kaikoura earthquake in Wellington, they had unfortunately had an earthquake in 2013. Actually, it's 2 earthquakes, so they had documented this area and had good surveys. So one of the most important things is this plot. And this is work with Professor Chubanowski and his student Ribu Dukal, as well as others, that have characterized that this area of the port had 200 millimeters of settlement, plus or minus. And we have then later put these CPTs in, and so we have 6 CPTs to characterize the ground conditions. So we cannot just say a site is a CPT, but we can say these CPTs capture the spatial variability, and so we can look at uncertainty at that level as well as the uncertainty of putting all this data together. And so now it's time to develop a CPT-based liquefaction ground settlement model. It's going to be very similar to what everyone has used in terms of volumetric strain in each layer times the thickness of each layer. This is what the relative density-based model that we developed, which works for sands, non-plastic silty sands, and non-plastic silts. Factor of safety, relative density gives us volumetric strain. We also have a model for the state parameter. You need the factor of safety against liquefaction triggering, and you either need the relative density or you need the state parameter to estimate the volumetric strain in each layer. To try to be mean-centered, we picked 2 methods that worked very well in most of our database, which is in New Zealand, the Boulanger and Idris and Robertson method to calculate the factor of safety against liquefaction triggering with a 50% probability of liquefaction being triggered, try to be mean-centered. What we lacked was confidence in a correlation to estimate the relative density for a silty soil. Most of that work is for clean sands. Well, Chris Markham and Christine Bazai had done very careful sampling. It was also consistent with the gel push sampling that was done. So the Dames and Moore gel push, several techniques were used to look at soils being high quality. You can never prove that a sample is undisturbed, but we looked at all the ways you could prove that it was disturbed, and it didn't show it was disturbed. So at least it's not, there's no evidence that proves it's disturbed, and we'll argue about how undisturbed it actually is. But these are high quality relative densities, and these are at sites where we have very good control because they have multiple CPTs. There were shear wave velocities, P wave velocity measurements done by UT Texas, tremendous characterization at these sites. And we see that this ratio goes down as a function of I sub C. For a certain relative density, the tip resistance is going to go down as you go to higher I sub C because the material becomes more compressible. And so you have to take I sub C to a factor of 3.5 times what you measure in terms of the normalized tip resistance to get an estimate of relative density. So this is our relationship. But we didn't want to just use our relationship. Robertson and Kabbalah have a very good relationship for clean sands, and they've done work on this type of problem and shown that their K sub C inferred correlation gives you a sense of how the relative density ratio should decrease with increasing I sub C. So we use the average of those two relationships. We expected the lab model to not work perfectly. It would have been overly optimistic and naive to think that a laboratory-based post-liquefaction reconsolidation model would work for reality. Now, we thought it should work better for hydraulic fill than it does for a natural soil. So we'll break the world into hydraulic fills and natural soils. But then we thought, we saw the layering in those silty soils, that what we're seeing at the element level in a test on silty soils is probably not going to be realized in the same magnitude in the field. And then there's also issues in terms of secondary compression and time effects that are more prevalent or more impactful for silty soils than they are for less compressible clean sands. And so we anticipated this, and we have a soil behavior factor that reduces the estimate of settlement in the field, taking the lab model, reducing it as I sub C increases. We did not expect to see a post-liquefaction magnitude factor. You know, liquefaction triggering has a magnitude scaling factor already in it, but that's for triggering. But the data clearly showed there was a trend where settlement, our model had a bias. So we thought about it, and so this is my conjecture, is most earthquakes that I've investigated, liquefaction happens early on or in the middle. It doesn't happen at the very end of the ground shaking. And so liquefactions happen, and then the longer we have shaking after the triggering, we will be generating pore pressures and dissipating pore pressures, and we will accumulate more deformation than if we just have liquefaction at the very end and there's no more shaking. So that's my explanation after the fact for why this makes sense to be there. Sometimes you have to listen to the data. So here's the model. It's volumetric strain. It's the thickness of the liquefiable layer. And we have a depth weighting factor. Under-Chetin proposed that in 2009. It doesn't make the biggest difference, but we thought it would be wise and prudent to keep that in there, and it does improve things. We have our soil behavior factor, and we have our magnitude factor. And then we calibrated it to the clean sand. Hydraulic fills are much closer in terms of how they're built and how they respond, their age, to the laboratory tests, and so there's no correction required there. Natural soils are different. And this is the calibration factor that I cannot fully explain on why we have to put that factor in there to get the lab tests to match up. I didn't expect them to match up exactly, and that's the number that results. Notice the standard deviation. They're lower for the hydraulic fill than the natural soils. That we did expect. When we build a soil uniformly, it should be less uncertain to predict what's going to happen than if nature builds that soil. And the values of the sigma are pretty much the same for relative density or the state parameter. So these models, the volumetric strain of non-plastic soils with uniform gradations, whether they are clean sands or silts, as long as they're non-plastic, you can use relative density. If they're slightly plastic, I think state parameter would work as well. The probabilistic CPT method can be used, and of course it's going to be consistent with our case histories. Otherwise, I wouldn't be showing it to you. Now ejecta-induced settlement to finish things off. It's the obvious where we have sand taken out from underneath the building. It's the most difficult because it depends on defects in the crust. Where there's a light pole, you have a cavity and you're going to have more ejecta than if you don't have that. This picture, this video was shot by a person. The landowner had already been through the Darfield earthquake and seen liquefaction, so they were educated on that. But the ground shaking had stopped, and much like the case histories by Hausner's and others, liquefaction ejecta kind of percolates and happens after strong shaking. Typically, it's 2 to 3 minutes when you read some of the post-earthquake reconnaissance observations. There's no pipe here. This is ground where the water pressure is high. A crack will be in the crust. It'll be a defect, or there'll be some crack created by the incoherent ground motion, and water will find a way forward or to the surface, and it will create the ejecta. So this is really a hydraulics problem, not just a solid mechanics problem. And so we know from looking at this, we have an initial total head for the hydrostatic case that's constant, so there is no flow. But the water pressure that develops in the liquefiable layer will create an excess head. Once we have an excess head, we have a differential head, and we have a gradient to enforce upward flow. Even this denser layer will generate some water pressure that has to then move up vertically. We decided to use the one-to-one line as an indicator of, do you have enough pressure, enough excess head to create artesian flow, for water to want to bring soil up to the ground surface. And to emphasize that, we took this excess head that we calculate, minus the head required for artesian flow. We square that to emphasize how important that is and integrate that to get the artesian flow potential. Let's look at 2 sites, Shirley and St. Teresa. Let's look at 3 of the earthquakes: the Darfield earthquake, the February Christchurch earthquake, the June earthquake. And there was significant extreme ejecta for Shirley and severe for the February and June earthquakes respectively. There was very strong shaking, actually slightly stronger than at the Shirley site at St. Teresa, but there was no ejecta. The LSN numbers were high. And so let's do effective stress analysis. The effective stress analysis is going to be done with open seas and with FLAC. We're going to use the family of models that Professors Boulanger and Cipatullo developed at UC Davis, PM4 sand and PM4 silt, with one PM4 silt with kind of more of a sand-like behavior and one PM4 silt that has more of a clay-like behavior. And this is one of the calculations. So this is the time history, that's input. This is the soil profile. You can see tip resistance and ISSMGE coloring. Red is more sand, blue is more silt. You can see the layering that we modeled in the modeling. This is the displacement time history. Notice that shaking induces high excess pore pressures. Water is flowing up. And notice how this secondary liquefaction, which is of primary importance here because it can generate the ejecta that's so damaging to the building, is actually increasing over time because we have water that is needing to flow up from below the liquefiable layer. And of course, we have the water that's flowing up from the liquefiable layer. This integration of this area squared over time is giving us this artesian flow potential. And notice that the artesian flow potential is higher after shaking stops. And it will continue to go along here, and it suggests a lot of ejecta. Contrast that with this case. This is St. Teresa. You can see that we can't model every little layer, but we put enough layers of silt between the sands to be able to capture the fact that, yes, there are layers that liquefy. They have high excess pore pressures. They get to a vertical effective stress close to 1. They actually, the deeper liquefaction layers, reduce the load on the upper soil, which is so problematic when it comes to liquefaction ejecta. And you have these low hydraulic conductivity layers between the layers that are generating high pore pressures that are not allowing the water to communicate vertically easily. When the water can communicate easily vertically, it will pool up, it will build up underneath the crust. Crust will have a defect, and then it will have the ejecta. In this case, we never exceed the artesian flow head, and so the artesian flow potential never exceeds 0. If we just integrate this artesian flow potential over the duration of the first 3 minutes of shaking, after that, I think things are breaking up, and using continuum mechanics is very tenuous. We see that it captures kind of the hydraulic gradient issue, the critical layer thickness, the volume of water. These are the EPIs that we calculated for these 2 sites for these 3 earthquakes. And when we calculate a high value, we had extreme ejecta observed. When we calculated a lower value, it was still ejecta, and there's a lot of cases where it's 0. And it resolves the issue with LSN overestimating things at the St. Teresa site, which is a highly stratified site. You should do effective stress analysis. You gain so much insight when you do effective stress analysis. But before you do that effective stress analysis, or on a typical project where you maybe cannot afford to do it, let's look at a CPT-based ejecta severity chart. And this is the work of Daniel Hudebrat and myself that was just recently published in the ASCE Geotechnical Journal. We really focus on resolving the stratified silty soil sites. LSN, as a comparison, has a range of none and minor at different LSN values, whereas this liquefaction demand parameter, largely because it's looking at hydraulic conductivity, and the hydraulic conductivity of the layer relative to that of clean sand. So it's a normalized hydraulic conductivity parameter that essentially is calculating liquefaction demand of 0. It also does a reasonable job at clean sand sites for breaking out extreme and severe cases from cases with none to minor. And so that's the basis of this liquefaction severity chart. In addition to demand, we should always be thinking about resistance. And so the crust does play a role. So let's integrate the strength over the thickness of the crust and get a resistance number. And the combination of those two are going to say that if you have a high liquefaction demand parameter, you will get extreme ejecta. If you have a low LD, liquefaction demand parameter, you should have none to minor. And the crust does play a role, especially as you get out to stronger and stronger crusts. So from this study, moderate to extreme ejecta largely occurred at the thick clean sand sites, which had these high liquefaction demand parameters. The none to minor ejecta occurred at the stratified silty soil sites, which had the low LD. Remember, buildings, defects, all those things can change it. So this is an indicator. It's not the truth, or it's hopefully a glimpse at the truth. So my final thoughts. So one, thank you for your attention. I'm indebted, I think we as a profession are indebted to the late Professor Harry Seed. He really did forge a way of advancing knowledge in geotechnical earthquake engineering. His integration of field case histories, experiments, and analysis should be emulated by us in the profession. and I've tried to do that with my students over my career. Liquefaction settlement mechanisms such as shear, volumetric, and ejecta have to be considered. The CPT is still my preferred way of characterizing the ground, but it should be coupled with cyclic tests. And we can do those on silty soils because we can retrieve those specimens and get good results. Do use effective stress analysis, not to get the right answer, but to gain insight and see what's important. But most important is geologic details matter. So going back to something I had learned a long time ago that unfortunately I had forgotten, I had to relearn, is take careful samples and look at the soil. The CPT is wonderful, and a lot of our techniques, shear wave velocities, are wonderful, but see what nature has actually built. And you can only see that with careful logging and geologic analysis. Thank you.